Welcome to the last class of our course. We have defined critical exponents for these equations, which are responsible for existence and non-existence of regular solutions. In this class, we are going to use their exponents to define singular and exterior domain solutions. A singular solution is just a solution which has a blow-up at zero. It can be of three types, either n-2 blowing up, when the solution leaves the point A0, alpha blowing up when it's issued from M0, and pseudo blowing up when it comes from a periodic orbit. As a first example, we can see that the stationary point M0, as far as we are in the region, in this range P larger than PS, is always a trivial singular solution for our problem. And it's alpha blowing up because it corresponds to this point M0. Recall that when we have P less than this number, equal, in the case of equality, we have M0 equals to A0, and in the case P is less than this number, we have M0 in the fourth quadrant. In this case, these numbers PS, they are related and they come from the Liouville result for super solutions in Rn, which says that we don't have positive super solutions for this problem as far as we are in this range P less or equal than PS A plus or minus depending on the operator. But we can also see this theorem working with the dynamical system approach directly, because in the case that we have P less than PS A plus, let us consider for instance the operator M plus. We know that in this case A0 is a source. So we have infinitely many trajectories which are going out from A0 and which corresponds to singular solutions to this problem, and singular solutions that blow up in finite time. So solutions in a ball, in this case in a ball minus zero. So we have infinitely many singular solutions of this type. When P is equals to PS, we still have infinitely many unstable directions. In that case, A0 is not a source because it has a zero eigenvalue, but we can see that, for instance, homoclinics like this are not admissible, and this is by the proof of the Dulux criterion. It works exactly as we did before. We can also see singular solutions when we are on the critical exponent. In this case, for the critical exponent for M+, we are seeing that M0 is a source, so we have infinitely many singular solutions with alpha blowing up. But we also have this periodic orbit, because this, since we have at this critical exponent, we have M0 as a source, the orbits issued from M0, they need to go somewhere, and they converge to a periodic orbit. But with this, automatically, the flow, which is subject to the Poincare-Bendixson theorem, requires the existence of infinitely many periodic orbits from this periodic orbit, such that the solutions are converging up to this region in order to have a density of orbits, because in each point of the flow we have this property that for each point that we take, there exists a unique trajectory passing through this point. And another example, which is very simple in this case, but just to to look at the singular solutions in this case is the Hannon equation. In the case that P is between PS and PA delta, we have seen that this is the flow. And it's interesting that in this case we have exactly one alpha slow decaying, alpha blowing up solution issued from M0, and we have exactly one with fast decay. And we have infinitely many alpha blowing up solutions of the ball. In the case that P is larger than the critical exponent for the Hannon equation, we are seeing here that we don't have singular solutions because here M0, we don't have periodic orbits, A0 at this point is a source, and actually the only singular solution is the solution given by the trivial one given by M0. As far as we are at the critical exponent for the Hannon equation, we know that we have the center configuration around M0, and so it produces infinitely many periodic orbits. But let me just point out that not all of them correspond to C2 solutions of our problem, because solutions like this, they oscillate between two trivial singular solutions in this form. And they do attain such infimum and such lim inf and lim sup infinitely many times. So the only way of doing this is by changing concavity infinitely many times. So the only ones which correspond to C2 solutions are the ones which cross the concavity line. Now let us see a counterexample of singular solution as far as we are in the supercritical regime, which is given by the fast decaying trajectory. Let us recall that for the operator M+, we have this critical exponent here and PPA plus here. Recall that when P is larger than this PP, we are in the range of slow decaying solutions. So M0 is a sink, periodic orbits are not allowed, A0 is a source, so we don't have any other non-trivial singular solution. What happens when we are in this range here of pseudo-slow decaying? In this case, the regular trajectory is converging to a periodic orbit, and if we have this fast decaying trajectory issued, which arrives at A0, coming from this periodic orbit, then a crossing would occur, and this is not admissible. So that's how we see that we don't have non-trivial singular solutions in this supercritical case. As I said, in this range in which we have pseudo-slow decaying solutions, since M0 is a source in this moment, we have infinitely many singular solutions which are issued from M0 and have a pseudo-slow decay at infinite in this way. Now what happens for the operator M-? Recall that the range of the operator M- is reversed from the operator M+, because we have PP minus on the left-hand side now, and this PA delta here. Recall that by the Dulux criterion, we have all this range on the left-hand side of PP and on the right-hand side of P delta, in which you don't have periodic orbit. And because of this, it allows us to define this critical exponent here, which belongs to F, which is unique and gives us the threshold between existence and non-existence of solutions as before. But what is interesting is that in the subcritical case, which is this region here, we can see that a periodic orbit is required because the regular trajectory is blowing up and M0 at this moment is a sink. So we need to have an alpha blowing up solution admissible for the fast decaying trajectory. And that's why this periodic orbit needs to appear. So from this, we have the existence of infinitely many pseudo blowing up solutions, which are singular solutions of pseudo blowing up type. We have infinitely many which arrive at M0 being with slow decay. We have infinitely many which are pseudo blowing up and solutions in the ball, like this gray here. And we have exactly one which is pseudo blowing up with fast decay. And with this, we have all types of singular solutions in one picture. To finish, let me just mention the Liouville result for exterior domain solutions in the critical or subcritical regimes. It's really simple because when we have a regular trajectory blowing up in finite time, this creates an invariant set at which a potential exterior domain solution cannot enter. So, in this case, exterior domain solutions are not admissible. And the same is true when we have at a critical exponent and an exterior domain cannot pass through this trajectory. With that and with some open problems, we finish this course. I hope you have enjoyed. See you next time.